Hello, welcome back. Sorry for the delay. Had a little family trouble at home in the morning. I had to take my daughter to school. Um, because and yeah, but we are just a little bit late, and so we're gonna pick up right where we left. Reminder that next week there's ISME, so I will be in Cape Town. If you're in Cape Town, come and say hi. Um, I'll be speaking on the Wednesday at the Night of Microbes event. So do show up for that as well if you wish. Otherwise, I'm happy to chat. Microbes. I'm happy to chat about quality estimation of high quality long read assemblies. I'm happy to chat about any of the work we've done, small peptides, semi-bin, anything, or just chat about what you've been doing. I'm always So without further ado, let me start. Let me do a recap of what we were doing before last week. So last week was a little bit slower than usual. We had a lot of sort of catching up, or I had to sort of get myself back into what we're doing. So as usual, everything's. So where to by point? Yes, no, sorry, because the camera's So everything's there on GitHub. There's a we stream everything in the channel. I try to minimize the amount of work I do on this project off stream. It also helps me to time box the amount. There's only so much I can dedicate to this project. But we also have an email list where I always post a recap every week. So if you've missed a session and you don't have the inclination to watch the whole stream, you can always just check the recap and check the emails. All right, so with that, let's see. So what did we do last week? So last week we did a couple of things. So we've been looking at whether we can use the size of the ORFs in a genome, and the fact that they might be exceedingly small or smaller than expectation as a way to estimate an excess of pseudogenes. So, and what we did, jumping ahead a bit too much here, and one question we've been dealing with is, okay, so what does it mean to be smaller than expected? So we need to define some sort of expectation, some sort of background distribution. And so the first thing was, okay, can we just plug into CheckM2's results? Because we've already run CheckM2, we continue to. I think we're not aiming to replace CheckM2, we're able to complement it. So any potential users of any potential tool that we develop will also very likely have run CheckM2. So it would be very nice if we could have something that just plugs into that, just takes those outputs and enhances them somehow. And so CheckM2 uses assignment of ORFs to KOs, and that's the basis. That's the basis for it. And so we already have for each genome an assignment of ORFs to KOs, and so that would be ideal. So all right, so now we have ORFs to KO. So we know in this genome there's ORF 1, 2, 3 is in KO 5, 7, and so we can ask, okay, so what's the typical size for KO 5, 7? And if it turns out that a lot of them are small, then maybe that's something, right? So we've been looking at these distributions, and we still need to define. Okay, we still need to define what's a typical KO 5, 7. And so we looked at using the same database that came with CheckM2 and use that as a background. And so there's a couple of reasons why that's not a very good idea. One of them is that it seems to include fragmented genes. At least some of them are very, very small, much smaller than you'd expect, and also it includes eukaryotic genes, right? So still, we're looking into this. We've been plotting this data in a couple of different ways, and this is what we did last week. So we took all the KOs. Well, actually, we take the KOs that are detected only one time. That's another complication factor there. But the ones that are detected only one time, are they? So what percentile are they? And then we just sort that. And so if we expect an overabundance of small KOs, so here, so the orange and the blue lines are the wild type and the 100 mutations in silico. Green is 1,000 mutations. You can see that there's this little bump where we have at the end. So this is Bacillus subtilis. In E. coli, the same. In Listeria, the same. Staph, the same. You can see the curves, and this is actually interesting. The curves, even the wild type curve, varies, and maybe Campylobacter, for our purposes, is the most worrisome in some sense, because the Campylobacter. So if we only had the blue curve, the Campylobacter, there's already some sort of overabundance of smaller than average genes. Actually, I'm not, and I mentioned this last week, I'm not aware that this is a known phenomenon, or it might just be my ignorance, but that, could it just be that, Campylobacter just has shorter genes on average for the same KO? Right, so that might be actually an interesting question to look at some point in the future. But for now, let's continue with something else we did last week, which is last week we downloaded, or we wrote the code to download the GMGC. Actually, so we had to look for this URL, but to download the GMGC version 1.0, 95% nucleotide redundancy removal, and only the complete ORFs. And we want the amino acid versions. And so it's actually sort of interesting that when we were publishing that paper, we had a lot of discussions with one of the reviewers as to whether the GMGCs would even include any fragmented genes, and we defended inclusion, and one of our arguments at the time, which I think is still valid, or I still agree with it, is that it's easier to start from something that includes everything, so we include everything, and then we can, when we do provide the subset, so for many uses it might be useful to have a subset, and so this would be one case, right? This doesn't invalidate having the larger data set. Right, so that's a little bit of an aside, but data. Okay, there it is. Okay, this is it, but just check that down. Okay, so we have that, and then we played around a bit actually, and we saw that and I think I saved it, node stream. Yeah, this is what we want to run. Something like this, right? Oh. Okay. Okay, but we don't want to run this on the command line. Let's do, okay, at some point we will, we'll have to figure out just okay. Okay, we saw also that diamond we have to have the matching version. So we're running the same version of diamond that comes with checkm2. So that okay, so this will work on my computer. Probably won't work on yours because you do not, unless for some reason your username is also this Pedro, that's not going to work on your computer. So let me just check how in Python. So I want to get the home directory in Python. I think that should be a okay, sorry. Yeah, that works. Yeah, that should work. Okay. All right. At least now, unless you've changed the number of where you want to store things, this is the default. Let me do 8 because we are going to. Okay, and yeah, okay. It's a bad name. So where have we outputs? Yeah, outputs. Yeah, this is not bad. Okay, this should. Okay, now I've called this jog file.py. Okay, so this is gonna take a while because this is 13G, it's still almost 100 million sequences. Oh, there it is. Okay, by the way, this thing that I did here, right, so this was, I could have also done this, or I could even have just done this actually. Could have even just catted it all to the, could even just done this, that would have been fine. So all I wanted to do was, so zcat is going to decompress and concatenate all of this, and gzip files, they have a checksum, which means that, if there's any errors in the files, well, it's not, unless you get very, very unlucky, if you have any errors in the files, partial, the most common type of file corruption is that the download didn't complete, so it was a partial download, and if that happens, then the checksumming will catch that. So we would have seen an error. So I just wanted to just double check and zcat. So I've actually advocated often that by default you should gzip or compress everything, even when the file space savings are very meager because of the checksumming. Because it's actually incredibly common that you have partial files. It's very uncommon that you have corruption within a file, right? That you have, file with 13G and somewhere in between, somewhere in the middle there's, but that does happen. Hard drives are, they're not infallible. Actually, they fail all the time. But it's very rare that happens. But it's, because normally when the hard drive does fail, what you get is, some sort of I/O error, rather than this silent data mutation. However, having a partial file is very, very common, and in formats like FASTA, it's very, you can have you can have a FASTA file that looks like a real file, right? If you have a bunch of genes, so here, if the file ends here, what you'd have is, first of all, you'd have this gene would be truncated, and then everything after that would not be there. And so you think you just have fewer genes, and one of them is slightly smaller, but this can very easily go undetected, right? So okay, so I'm calling this jug file. I'm not sure. All right, why not? Okay, frankly, everything we're doing so far is still in this exploration phase. If we ever were to move towards, having something concrete, we'd probably have to clean up everything anyway. But let's just call it jug file. So in jug, if the okay, all right, let's figure that out in a second. So in jug, before we've been doing things like this, jug status download data or simulate, right? And this also works like with jugfile.py, works exactly the same. But if it's jugfile.py, we can also just leave it off and have it be like this, right? Works perfectly fine. Right, so Diamond is running. Should be running in the background. Frankly, given that it took a few minutes just to run JZip or Zcat, it's probably, I guess in Australia I should say Zcat. It's probably not going to finish. Now it will probably run for a while. All right. So in the meanwhile, let's just play around a little bit with looking at the data. So let's see. We still have a lot of time. Let's just look a bit at data. Let's just document everything. By the way, notes, stream notes. Okay. Oh, there. Okay. Today is 13. Okay, I guess 13. Okay, we don't need this anymore. Okay, all right. So that let me just check. So yeah, using it as a database is probably still going to be something we do next week, or actually the week after, because we can't really do. It won't finish today. So Diamond probably is going to run, several hours, but it will run. And I'm running. So everything for this project, I'm always running it on my laptop, which is a pretty nice laptop. It's new-ish. Well, I guess it's. I got it when I got to QT, so that was last year. But it is really just a standard sort of laptop. It's nothing. So we do have other work. We've been working with for example, mapping to the GMG, mapping short reads to the GMGC. We've been playing around with doing that with Stroboline, and and there, we need 300 G of RAM, which we're hoping to get down to only 200 around that. That would be great if we could do that. But obviously that's not something that you can do on your laptop. I mean, I don't know. Maybe some of you have a 1 terabyte RAM laptop, but for this project in particular, for everything we're streaming, I do want to be something, and this is a constraint, that if you have access to a standard consumer laptop, you can run everything I'm doing here on your own. So everything's on GitHub. You can just maybe some things will be running overnight, but you can run everything. Annotate GMGC v1 with OKOs, use and process. Okay, and we're using the same process as checkm2 because doing so, we hope that this way we can later reuse the checkm2 outputs. Okay, right. Let's see. Okay, let's look at. So this is the length by KO. Is the. Just gonna import all of this. Okay, so this is what we've been working on the last several sessions. So, right, so we process the outputs of checkm, and okay, let's just get. Okay, we'll load. Okay, let's load. Okay, I'm just adding. Let's look at 2000 mutations for. Okay, I've been. Hello, Sean. Hi, Sean. So here, let's. Sorry. Actually, so now I was just trying to see what happens if we push the. If we look at 2000 mutations, I think you know, this is probably the right range. Hundreds to thousands, low thousands of mutations is the right range. You know, the beginning of the project we were looking at this simulated data with, you know, tens of thousands of mutations, and that's probably, you know, that's probably not realistic. I mean that's, but 1,000 mutation, yeah, that seems pretty much something that could happen. Let's see, what it, oh. Okay, so we had here. I just wanted to see what happens with 2000. At some point this becomes, right, at some point this is going to become impossible to really, you know, this is not scalable code, so to speak. Right. I mean, yeah, when you're copying and pasting a lot, this is not. Okay. This is not great. Okay, this is now going to be a bit extra slow because we're still running Diamond. We're running OBS, which always slows everything down. So if you run this, I mean, and I've had this experience a lot when I now I know to expect it, but I've had this experience a lot where I start by testing something out offline. It runs really fast. It runs a few seconds. Then it's like, oh, I'll show it off on the video, and then I go show it off on the video, and it takes minutes because now OBS is running and messing everything up. Right, so, or not messing everything up, but just making everything slower. Alright, so okay, right, alright, so here again you can see a decline, right, but it's subtle, right? And that's because, and this is selecting only the ones where we've purposefully selected them to be different. If we include everything, then it's this is everything. Okay, I'm gonna do this thing. So if I align, if you look, okay, I'm gonna make this bigger. So if I use the window as to show that line, to show that horizontal line, there's a decrease there. I mean, but if I only showed you this rightmost one, you wouldn't pick it up, right? You wouldn't know. It's impossible. Okay. I'm just gonna close all of gotten a bit. Right, this is the plot from before. Okay, so there's some. So the red ones are the ones that go up. Right. So here, I mean, so maybe let's just look at those a little bit. Okay, I'm actually going to do okay, there's no show there. Okay. Alright, so here. Okay, so here went from 1,000, 1,115 to 1,300, right? So that's okay. Actually, since we're waiting for the other thing to run, right? What I actually want to do is I want to look at sequences. Right? I want to look at actual nucleotides and amino acids. And so what I want to do is I want to look at, let's look at two extremes actually. Let's look at this one and then let's look at this one. Right? But let's start with this one. This is actually a nicer extreme to look at. So what I want to see this. which meaning, okay. Right. So we're just exploring for now. I have no idea. Sometimes I find that it's nice to just have a bit of that exploration helps. Okay. Okay, there's no show. I don't know where. Okay, so right now we're not writing code to keep. We're writing just code to really just write. Yeah, this is what we want. Okay, not writing code to keep. We're really just writing code to export the data. Okay. So simulated outputs. What are we looking at? We're looking at E. coli. Okay, yes. Outputs. Check M to E. coli. Protein files. We're okay. Sorry, there it is. It's not a partial gene. There it is. Okay. Okay. Right. Oops. Sorry. That's. Okay, there it is. This is okay, and that one we're looking. Okay, here. Wait, what? Oh, sorry. We were looking. Okay, we were looking at the 2000. Yes, the 2000. It's this one. Okay, so. Okay, same. Nope. Wait, actually, yeah, they're same. Not same. Okay. There it is. A to V, and then a bunch of randomness, which probably Okay, I don't know what this is. I'm gonna remove this. Okay. Oh yeah, there was. Okay. Okay. I'm really just playing around with stuff for now. Okay. Okay. So I'm gonna. Okay, so I'm just running this. So this is a sequence from E. coli. And now, so at some point what we did is so previously we used to create these mutated files on disk, but this was a bit annoying because, first of all, it just led to a lot of files on disk. That was, it's not even first of all, that was the main reason. That was, or even the only reason. So here I'm just gonna say, but the other, actually there's another reason, which is that it's very easy to do this. Well, not. Alright, it's okay. It's not so difficult to do this. Maybe not very easy, but not so difficult. To recreate them, and this should be. Okay, I'm gonna just save. We'll clean this up later. So with Git, we don't need to worry about these things. We will clean up everything later. All right, so okay, so this is 1781. It's at these positions. All right, so let's just load the data. I'll type. Okay, this should have been. Okay, what was? Okay. Right. This is. I think it's this. This is correct. Because I think this prodigal uses 1 base coordinates, so we need to adjust for that. So position 1 becomes position 0, but I think prodigal uses from here to there inclusive, and we want to use from here up to, but not including there. So I think this is correct. So if you do this, let's just quickly check. This should be divisible by 3. Yes, that is correct. And on the other genome, so you can see that it's similar, right? But it's not the same, because as we introduce mutations, they are off by, in this case off by 3. And we need to let's do this. Okay, so wait, is this correct? Right, so it says -1. So I think this means it's the opposite strand. Let me just check. A to T, C to G, G to C, A to T to A, and then this would be correct. Yeah, it seems off, to be honest. Yeah, there's something off here. Even like this. No. This is off. This is right. The one. Okay, there's something off here. Right, so this is. Okay. This is. Okay, this works. Sorry, I'm a little bit. I'm a little bit confused. What's going on? TCG, okay. Okay. Right. First of all, those should be the same. This should be the. Right. Okay, let's just. Okay, let's do this. I really just want to look at the sequences, just to develop a bit of intuition of what's going on. Okay, this works. Okay, so we have the okay, so that's there. Okay, this is here. All right, so this is not. This sequence. Okay. Something in the. Okay, yes, obviously. Wait, what? Okay, there's something. Okay, I'm not sure. Okay, I'm not sure how this is. Right? Am I? Okay, yeah. Okay, right. I'm not sure how this is supposed to work. Okay, let's look at the 2000. Yep, okay, so this is not, it's not surprising because this is indeed a deterministic process, so we should just be able to rerun it and get exactly the same thing a second time. And now this is what. Okay, and now all right, now let's use UBI pairwise sequence. Okay, yeah, I even have it here. UBI pairwise sequence alignment. Okay. PI 1 and 2. Okay, so there should be okay. Oh, surprised. Oh, okay, maybe not surprised. Maybe not surprised because I messed this up. Okay. this is the there it is, actually. Right, there's the frame shift. Okay, so there's one frame shift there. And then everything gets messed up. And then eventually this frame shifted sequence hits TAA. Alright, this would make some sense. Okay, that this, alright, this is the I don't understand why. I don't understand these coordinates. Something. Something at the start of the sequence. Oh. Oh, okay, this actually explains some. Oh, okay, this actually does explain things, okay. Okay, this actually does explain what was going on. Yes, okay, yeah, this is makes perfect sense. Makes perfect sense. So this is the perfect sense. So this, okay, these are the coordinates. Okay, okay, this now makes perfect sense. Yeah, this is okay, and then this. Oh. This probably, yeah, probably like this. Okay, actually, yeah. Okay, this makes perfect sense now. All right, there's still some adjustment there with the original first codon. The first codon should be the methionine. But yeah, but now, yeah. So there was the header. Okay, so this is what happens. There's a T there, extra T, frame shift, and then here, oh, TAA should be the final codon, but now it's reading sequence wrong, and the sequences as well. So let's just look at this. the sequence says, yeah, look good. And then here, complete rubbish until the end. And then early stop codon. Or sort of a mid stop codon. Right, okay. I guess, yeah. I guess there's a natural asymmetry. There's a natural asymmetry because so if we look at the ones, yeah, so we were doing this, right? Right, and here, this was an extreme case where 200, this ties a little bit into our small protein work because, okay, so here we have, so for the mutated version to be longer than the wild type, what it means is that somehow we missed the right stop codon, but just sooner or later, we hit we're always going to hit something that looks like a stop codon, even if it's not the real stop codon. Right. So yeah. So what I mean this relates to our small protein work is because just if you have random DNA, you end up with random. So here you're reading random frame shifted DNA. So you end up reading, and it's like so if you have random DNA, how fast do you get the stop codon? And you actually get it quite fast. It's rare to have random DNA that lasts for hundreds of base pairs, and and this is the outlier. So these are the outliers where for you had all of this random DNA or being read out of frame, and somehow managed to go for 200 base pairs without getting even a single stop codon. But this is because we looked at the outlier. Okay. But it's interesting. It's interesting. It's a good intuition to have, that the fact that there's the fact that having an increase in size is much more difficult to have a large increase in size, whereas if we do it the other way around, right? This is okay. Let's just plot that actually. List. Okay, this is actually quite terrible. Alright, so this is it's about visualization, but blue would be the increase, and you can see there's a couple of outliers there, so if you're looking, but then the decrease, first of all, we have a lot more, and then the upside is so you can easily get 3,000 base pairs off of a gene by just getting a very early stop codon, but we do not get 3,000 or even 1,000 or even a few hundred 200 really is the upper bound. I mean, we've looked a bit into this in our small protein work. This is all going back, now decades, where, if you just have random DNA, how fast do you get the stop codon? It's actually, the expectation is that in 20 something amino acids, you will get one of them will be a stop codon. But then if you have a genome, right, this is, what is the maximum over a genome, then it's a couple hundred, so 100 something, 200 I think is, I'm speaking from memory, I haven't looked at this in several months, but yes, I think that distribution you're seeing here in blue, this is pretty much the sort of random DNA expectation, is that yes, most of them are going to be very low, and then in a genome with 4 point something megabase pairs, you're going to have a couple that are 100 amino acids, and 216 seems like a good upper bound, right? And then, so this was, so we were just playing around, we were basically not even paying too much attention to what, just writing code in the middle of these files, so let's just throw it away. There's really nothing here I want to keep, not even in the work in progress. Okay, this was really, maybe I want to keep it just to do the recap. I'll keep that for the recap, but that will be all. Okay, I want to save this for the recap. Let's just see notes. Okay, okay, we did this, and then export plot data. Right. Vision of okay, this is not very precise, right? But right, document. Okay, that's it. I will push that to GitHub. So as usual, everything is up on the everything's up on GitHub. Everything have the mailing list. Right, so next week I'm off to Cape Town. Come say hi if you're in Cape Town. And otherwise, I'll see everyone in 2 weeks.